Tonight, we're going to look at the widest and thinnest structure you can see from Earth with a small telescope. Saturn's rings extend up to 282,000 kilometers from the planet, yet the main ring sheet is typically about 10 meters thick. That proportion is so severe that most pictures cannot show it honestly. The rings seem broad and solid because we usually see their face. Turn them edge on, and the great bright disk becomes a line so narrow that it can nearly disappear. Imagine reducing the full span to the length of a large dining table. At that scale, the ordinary thickness would be much less than the thickness of a sheet of paper. The familiar image of Saturn is therefore a trick of perspective. What looks like a wide silver roadway is an immense population of separate objects sharing a plane, each one falling around the planet on its own orbit. But how can a structure hundreds of thousands of kilometers wide remain only meters thick, while billions, and likely trillions of pieces continually move through it? By the end of tonight, you're going to understand exactly what the rings are made of, how their named bands and divisions fit together, and why gravity can flatten, carve, wrinkle, and slowly remove a disk that appears almost permanent. Before we get started, if you love exploring the quiet architecture of the solar system as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Saturn itself is already a world of large numbers. Its equatorial diameter is about 120,500 kilometers, roughly 9 times Earth's. It turns once in only about 10.7 hours and travels around the Sun in about 29.4 Earth years. The visible rings make that giant planet look almost delicate. Their broad face catches sunlight. Their particles scatter it. Their gaps trace dark curves that appear fixed from a distance, even though every piece is moving. There is no single ring spinning like a wheel. There is no continuous slab. There is no floor. There is ice, dust, rock, gravity, and time. The apparent object is a pattern held together by countless separate paths. That distinction changes the journey. To go inside Saturn's rings is not to enter a tunnel or land on a shining band. It is to cross a remarkably flat swarm. The scale is planetary. The thickness is architectural. The motion is orbital. And from the first edge to the last, almost everything depends on where you are standing in Saturn's gravity. The first useful view is the one that seems to show the least. Seen from above, the main rings display their full circular geometry. Seen edge-on, they narrow into a pale line crossing Saturn's equator. During a ring plane crossing, Earth passes through the plane from which the rings are viewed. Their broad reflective surfaces turn away from us, and the system can become difficult to see through a modest telescope. This disappearance is not perfect. The rings contain dust, clumps, waves, and small moons. Some material rises above and below the ordinary plane. Scattered light still finds irregular paths, yet the sudden loss of that enormous bright surface reveals its defining proportion more directly than a face-on portrait ever could. You could travel vertically from well below the rings to well above them in the time it takes an elevator to cross a medium-sized building. Traveling across their radial extent at the same speed would demand years. One direction belongs to human distances. The other belongs to worlds. The word inside therefore needs care. The main ring sheet has no enclosing walls. Its upper and lower boundaries are not sharp surfaces. Particle density gradually changes with height, and the exact thickness differs from place to place. NASA's rounded description of about 10 meters captures the typical vertical scale of the dense main rings, not a universal ceiling imposed on every grain and moonlet. Most particles remain close to Saturn's equatorial plane because their orbits have very small inclinations. A particle on a tilted orbit crosses the plane, rises above it, descends through it, and rises on the other side. Collisions with neighbors gradually reduce those vertical motions. The swarm loses energy from its random movement while retaining the organized energy of orbit. Over time, a thick cloud becomes a thin disk. The same process helps explain disks across astronomy. Material around young stars settles toward a common plane. Debris disks flatten. Galaxies develop thin rotating components, though their scale and physics differ greatly from Saturn's rings. Whenever many orbiting bodies collide or otherwise exchange energy, orderly planar motion can survive while disorder is reduced. Saturn offers that principle in a form close enough to map. The ring plane is aligned with the planet's equator. Because Saturn's axis is tilted by about 26.7 degrees relative to its orbit, sunlight reaches the upper and lower faces in turn as Saturn moves around the Sun. Roughly once every 15 Earth years, at equinox, the Sun shines nearly along the plane itself. Then the broad bands dim. Long shadows emerge. Small vertical structures reveal themselves. The rings become a line, and the line becomes a measuring instrument. The rings entered human astronomy as a problem before they became an icon. In 1610, Galileo Galilei turned a telescope toward Saturn and could not resolve a clean disk surrounding the planet. His instrument showed a central world accompanied by two strange forms, one on each side. Saturn seemed triple. As the viewing geometry changed, those side forms weakened and disappeared, then returned. The reason was the same thinness that still complicates pictures today. When the rings were more open to Earth's view, Galileo's small telescope gathered light from their broad faces, but blurred them into attached lobes. When they turned edge on, too little bright area remained for his instrument to separate. The object itself had not gone. Its orientation had changed. Christian Huygens produced the decisive geometric interpretation in 1659. Saturn, he proposed, was surrounded by a thin, flat ring that touched the planet nowhere and was inclined to the ecliptic. That model turned a sequence of puzzling appearances into one coherent structure. The ring could open, narrow, vanish, and return because Earth and Saturn continually changed their relative positions. Giovanni Domenico Cassini then found in 1675 that the ring was not uniform. A dark division separated an outer bright region from an inner one. The broad gap now bearing his name showed that even Huygens's elegant disk contained internal structure. Those early observations established three facts that remain central. The rings are separate from Saturn. They are thin enough for perspective to transform their visibility, and they are divided into regions rather than built as one continuous band. Centuries of improved telescopes added narrow ringlets, gaps, and changing brightness. Pioneer 11 passed Saturn in 1979. Voyager 1 and Voyager 2 followed in 1980 and 1981, revealing spokes, intricate waves, and shepherding moons. Then Cassini entered Saturn orbit on July 1, 2004, beginning more than 13 years of close observation before its mission ended in September 2017. From Earth, a ring edge is a line. From a passing spacecraft, it becomes terrain without a ground. Cassini watched starlight pass through different bands. It measured temperatures. It imaged particles indirectly through waves and shadows. It saw moons giving material to rings and rings coating moons. The historical progression moved steadily inward. First came the outline, then the division, then the individual bands, then the particles and the forces between them. Each step replaced a solid-looking object with a more dynamic one. Saturn's rings became less like an ornament and more like a system. The spacecraft era also changed the kind of evidence available. Pioneer 11 supplied the first close reconnaissance and found the narrow F ring. Voyager resolved thousands of features and showed that temporary spokes could cross the B ring. Cassini stayed long enough to watch the system change with season and viewing geometry. A flyby can reveal a place. An orbiter can reveal behavior. Cassini carried cameras, spectrometers, a radar, fields and particles instruments, a dust analyzer, and a radio science system. No single instrument produced the modern ring story. Images located patterns. Spectra identified water ice and contaminants. Thermal measurements followed warming and cooling. Dust impacts counted incoming particles. Radio tracking weighed the system indirectly through gravity. The long mission also prevented one moment from becoming the whole interpretation. A spoke absent in one season could return in another. A propeller could be followed around Saturn. The same ring edge could be photographed under high sunlight and then under equinox illumination. Change became data rather than noise. That time dimension is essential. The rings seem fixed in a portrait because their broad architecture outlasts the exposure. At particle scale, an orbit can take hours. At mission scale, moon-driven patterns shift. At geological scale, the whole disk spreads, darkens, loses material, and perhaps creates moons. Every observation chooses one clock. The next step is to build the map. Ring names do not run outward in alphabetical order because the letters were assigned mainly in order of discovery. Beginning near Saturn and moving away, the sequence is D, C, B, the Cassini Division, A, F, G, and E. Far beyond those lies the extremely faint Phoebe ring. The D ring is dim and close to the planet. The C ring is more transparent than the great bright bands beyond it. The B ring is the broad, dense central presence in most familiar images. Outside the B ring lies the Cassini Division, about 4,700 kilometers wide. It appears dark, but is not empty. Beyond the division is the A ring, crossed by narrower gaps and shaped by nearby moons. The F ring is a narrow, restless strand just beyond the main rings. The G ring is faint and dusty. The E ring is vast and diffuse, supplied largely by icy material from Enceladus. Each belongs to Saturn's ring system, but they do not share one density, one source, or one behavior. A traveler looking down from above would not see neat printed boundaries. The divisions are changes in particle density, size, and optical depth. A dark region can still contain countless orbiting pieces. A bright region may be partly transparent. At different viewing angles and wavelengths, the same ring can reveal different patterns. The main rings occupy a comparatively compact zone near Saturn. Their total visible span is enormous, but their radial width is assembled from thousands of ringlets. Some are only kilometers wide. Others extend across tens of thousands of kilometers. Waves compress and spread their particles into alternating bright and dark stripes. The names help because the raw detail is too rich to hold at once. A, B, and C provide the broad architecture. The Cassini Division gives a prominent landmark. Encke and Keeler identify narrower gaps within the A ring. Pan travels through the Encke gap. Daphnis moves through the Keeler gap. Prometheus works along the F ring. Enceladus feeds the E ring from far outside the bright main sheet. Even the phrase ring system can mislead if it suggests a fixed diagram. The boundaries respond to resonances. Dust is created and removed. Moonlets disturb their neighborhoods. Electromagnetic forces lift small grains into temporary spokes. Seasonal light changes what cameras can detect. The map is stable enough to name and active enough to keep changing. Letters mark regions. Gravity writes the detail. The most important correction comes next. A ring is not a surface. Close up, it dissolves into separate bodies moving through empty space. Most are made predominantly of water ice, mixed or coated with smaller amounts of rocky material and dust. Their sizes range from particles below a grain of sand to chunks comparable with a house. A smaller population reaches much larger scales. If you approach from above the plane, the bright sheet would gradually separate into flecks. At a great distance, scattered sunlight blends them. At closer range, darkness opens between them. The exact spacing varies enormously. The opaque B ring is more crowded than the C ring. A narrow, dense wake differs from a diffuse, dusty ring. There is no single experience that represents every region. The particles do not remain fixed relative to one another. Every one follows an orbit determined mainly by Saturn's gravity. A piece closer to Saturn completes its path faster than a piece slightly farther away. Two neighboring particles can therefore pass one another, even when both move in the same direction. Collisions occur at comparatively gentle relative speeds in many parts of the disk, though local disturbances can make the environment more energetic. Standing is the wrong physical idea. A boot placed on one chunk would share only that chunk's immediate motion. Nearby pieces would trace their own paths. A large body could carry loose material temporarily, but it would not turn the surrounding swarm into ground. The next object might be meters away, hundreds of meters away, or hidden within a dense stream of smaller pieces. The ring plane is also not a safe corridor. Spacecraft planners treat ring particles seriously because even small grains can damage a vehicle at high relative speed. Cassini's daring final orbits pass through the gap between Saturn's atmosphere and the D ring, not through the dense A or B rings. Its antenna was sometimes oriented as a shield against possible particles. This is the quiet paradox of the view. Saturn's rings look continuous precisely because individual pieces are too small and too numerous to resolve. A cloud looks smooth from afar for a similar reason, but a cloud is made of droplets suspended in gas. A ring is made of solid bodies in orbit. From a distance, silver. From nearby, separation. From within, motion. The transition from surface to swarm would not happen at one sharp distance. Resolving power depends on particle size, lighting, and the instrument doing the looking. A bright wake might remain visually continuous after sparse surrounding regions have separated into points. Backlighting might reveal dust invisible under direct illumination. A radar or radio beam might detect bodies that eye cannot distinguish. Human vision also favors the broad pattern. The brain joins nearby bright marks into bands and follows long edges across the frame. That perceptual continuity is useful from Earth, where Saturn may occupy only a small telescopic image. It is physically incomplete at local scale. A dense ring still contains collisions. Two particles can meet because their orbits differ slightly in eccentricity, inclination, or speed. A collision can produce smaller fragments, join porous frost temporarily, or change the spin of both bodies. Repeated encounters continually revise the population. Some surfaces are young even if the material inside them is old. The lack of a surface does not make the ring insubstantial. Its particles carry the measured mass. They exchange momentum. They block light. They tug on spacecraft and moons through gravity. The correction is not that the rings are an illusion, it is that their reality is granular rather than continuous. Water ice controls the ring's brightness. Clean ice reflects sunlight efficiently, giving the main rings their pale appearance. Yet the ice is not chemically or visually uniform. Dust and darker contaminants alter color and reflectivity. Particle surfaces are continually processed by radiation, collisions, micrometeoroid impacts, and exchanges with Saturn's moons and magnetosphere. Cassini used several kinds of observation to separate these effects. Its cameras recorded fine structure. Spectrometers measured how the rings absorbed and reflected different wavelengths. Radio signals pass through the rings toward Earth, with different frequencies responding to particle populations in different ways. Starlight and sunlight viewed through the rings revealed optical depth, composition, and distribution. Size matters because light interacts differently with a dust grain, a fist-sized block, and a house-sized mass. Small particles can be pushed by electromagnetic forces more easily than large ones. Large embedded bodies generate gravitational wakes. Medium-sized pieces dominate collisions and reflected light in different regions. Imagine a column drawn vertically through the B ring. The total material along that line could block much of the light behind it, yet the column is not filled continuously. Ice occupies part of the volume. Empty space occupies the rest. The phrase optical depth describes how strongly the population blocks or scatters radiation along a path, not how solid it feels. The B ring can appear opaque from many angles while remaining a swarm. The C ring can transmit more light while still containing an immense number of particles. The E ring can be almost invisible in ordinary reflected light, while spreading through a huge volume around Enceladus's orbit. Ring color also carries history. If dark interplanetary dust continually lands on bright ice, the surfaces should gradually become less clean. That expectation is one reason scientists have used contamination to estimate an exposure age. But the conversion from brightness to age depends on how much dust arrives, how impacts redistribute it, and whether contaminants remain mixed with visible ice. Those dependencies will matter when we reach the unsettled question of origin. For now, the simplest fact is enough. The rings are not made from one thing in one state. They are a population. Their particles have sizes, surfaces, compositions, and collision histories. Sunlight turns all of that complexity into the pale bands visible from Earth. Sunlight can make the same population look different from opposite directions. Viewed with the sun behind the observer, large bright surfaces can dominate. Viewed toward the sun, very fine dust can scatter light forward and become unexpectedly visible. This is how diffuse material that seems absent in one image can surround Saturn in another. The rings also display subtle color differences. More contaminated regions absorb and reflect wavelengths differently from cleaner water ice. Color-enhanced Cassini images amplify those distinctions for analysis, but the natural view from Saturn's cloud tops would remain mostly pale. The scientific palette lies inside small spectral changes rather than vivid painted bands. Surface texture matters as well. A smooth slab, a porous frost-covered aggregate, and a rough fragment can share composition while reflecting and storing heat differently. Thermal observations can therefore complement spectra. A particle that cools slowly may be larger or denser inside than one that rapidly follows the changing sunlight. Every instrument sees a selected property. Visible light favors reflection. Infrared light follows temperature and composition. Radio waves probe particle sizes and opacity. The ring itself stays the same moving population while each method extracts another layer of its history. The central motion of the rings is not Saturn's rotation. It is orbit. Saturn turns in about 10.7 hours, but ring particles circle according to their distance from the planet. The closer a particle is, the stronger the gravitational pull and the faster the orbital speed required for a stable path. This creates differential motion across every radial neighborhood. An inner particle advances relative to an outer one. If a group is stretched across several distances, Saturn's gravity gradually shears it into a long arc. A compact cloud does not remain compact unless its own gravity or another force binds it strongly enough. The effect explains why a painted mark could never remain a painted mark across a broad ring. Place an imaginary straight radial line through the particles. Minutes and hours later, the inner end has moved farther around Saturn than the outer end. The line becomes a curve. Continue, and the curve wraps into a spiral. Collisions and repeated orbital encounters eventually spread the pattern. The same shear shapes the response to moonlets. A small embedded moon perturbs particles on both sides of its orbit. Material nearer Saturn passes the moon differently from material farther out. The disturbance opens paired gaps and wakes that look like a propeller when viewed from above. The pattern travels with the moonlet, even though it does not spin like a physical blade. Orbital speed also sets the language of gaps. A moon does not need to sweep a lane clear like a plow. Its repeated gravitational encounters can redirect particles. A distant moon can act through resonance, applying small regular pulls at the same orbital phase until the accumulated effect becomes visible as a wave or boundary. In this environment, a minor difference in radius becomes a difference in timing. Timing becomes repeated geometry. Repeated geometry becomes structure. Saturn's ring patterns are therefore records of motion rather than markings laid on a disk. The Cassini division persists because orbital dynamics continually organize its population. Density waves travel because particles are periodically compressed. Sharp edges survive where gravitational forcing balances spreading. Every visible stripe contains two scales at once. There's the speed of an individual icy body, often many kilometers per second. Then there's the slow evolution of the collective pattern over months, years, and longer intervals. The particles race. The architecture appears calm. The thinness follows from what collisions remove and what they preserve. Start with a broad cloud of particles orbiting Saturn on paths tilted at many angles. Each orbit still passes near the planet, but the paths cross one another in 3 dimensions. Collisions are frequent. When two icy pieces strike, they can bounce, chip, deform, or fragment. The encounter converts some organized motion into heat, sound, rotation, and smaller debris. Random vertical motion is gradually damped. A particle that once climbed far above the equator returns with less of that inclination after repeated collisions. Another that moved on a slightly eccentric path loses some radial wandering. The common circular motion around Saturn remains because the swarm retains angular momentum. What fades is disorder. The result is a disk centered on the equatorial plane. It is not absolutely flat because particles continue to collide, moons continue to stir them, and waves lift material locally. Yet the ordinary vertical scale becomes tiny compared with the radial one. Saturn's rings extend up to 282,000 kilometers from the planet, yet the main ring sheet is typically about 10 meters thick. That ratio is not maintained by a rigid support. It is continually produced by interactions. Gravity draws every particle inward. Orbital motion carries it sideways. Collisions reduce deviations. Saturn's equatorial bulge and the gravitational influence of moons add smaller corrections. Together, they create a shared plane without a shared surface. There is a useful difference between flattening and compression. The particles are not pressed into a solid layer by weight from above. Most of the ring volume is still empty. Instead, their orbits become aligned. The thinness belongs to the distribution of paths. If a disturbance lifts particles a kilometer above the plane, those particles can remain on inclined orbits for a time. If collisions are weak in that region, the structure may persist. If collisions are frequent, vertical motion is damped again. The disk remembers the disturbance through waves and then gradually restores its ordinary form. This balance explains why exceptional mountains of ring material do not invalidate the typical 10-meter figure. A calm sea can support a wave taller than its average surface roughness. The wave is real, and the calm reference is still meaningful. Saturn's rings possess local relief generated by moons and impacts inside an overwhelmingly thin orbital sheet. The broad disk is a long-lived pattern created from small corrections repeated without rest. No architect, no platform, only gravity, collisions, and an immense number of separate returns to the same plane. The name journey begins close to Saturn with the D ring. It is the innermost major ring region, faint enough that it can disappear in ordinary portraits dominated by the brighter A and B rings. Its particles occupy the space above Saturn's cloud tops, inside the C ring, where the planet's atmosphere and magnetic environment exert increasingly important effects. The D ring is not a clean band with one edge and one texture. It contains narrow ringlets and diffuse material. Cassini detected corrugations there, a pattern resembling a vertically rippled sheet. Such a pattern can arise when the ring plane is disturbed and the tilted particle orbits gradually wind into a tighter spiral because orbital precession varies with distance from Saturn. During the 2009 equinox, low sunlight made these small vertical changes easier to see. A corrugation known in the D ring extended through neighboring regions over thousands of kilometers. The height was modest compared with the later Daphnis structures in the A ring, yet the reach of the pattern showed that a disturbance could write across more than one named zone. The D ring also matters because Cassini eventually traveled between it and Saturn. During the grand finale in 2017, the spacecraft made 22 passes through the previously unexplored gap between the innermost ring and the atmosphere. The route provided measurements of gravity, magnetic fields, dust, and material falling from the rings. That gap was not treated as empty in the absolute sense. Mission controllers used Cassini's large high-gain antenna as a shield during early crossings because a small particle at spacecraft speed could cause serious damage. The successful passages showed the region was navigable under the chosen trajectory, not that it contained nothing. Looking outward from there, the bright system begins gradually. First faint material, then the more visible C ring, then the dense B ring and the great division that carries Cassini's name. The familiar face of Saturn builds layer by layer. The D ring remains a quiet threshold. It is where the ring system approaches the planet closely enough for lost processes to become tangible. Some material spirals inward, some enters Saturn's atmosphere. Some carries chemical signatures that Cassini could sample during its final months. The rings begin not with a wall, but with a thinning population. Beyond the D ring, the C ring becomes easier to see and easier to see through. Its lower optical depth gives it a gray, translucent appearance beside the bright B ring. Older observers sometimes called it the crepe ring because Saturn could remain visible through its material. The name captures the view, but the physics lies in the density and distribution of particles along the line of sight. The C ring contains numerous plateaus and ringlets. A plateau is a region that appears brighter or denser than its surroundings, often with comparatively sharp boundaries. These features complicate any simple progression from empty inner space to a solid-looking outer band. Density rises and falls. Particle properties change. Waves move through the population. Some of the most revealing waves in the C ring are connected not to an external moon, but to oscillations within Saturn itself. The giant planet vibrates in subtle global modes. Those variations in gravity can resonate with ring particles and create spiral density waves. In that sense, the rings serve as a sensitive recording surface for motions hidden under Saturn's clouds. This field is called ring seismology. Earth scientists infer a planet's interior from seismic waves traveling through rock. At Saturn, no solid surface carries an ordinary seismometer. Instead, researchers read patterns in the rings. A frequency inside the planet can leave a repeated structure outside it, translated through gravity. The C ring is especially useful because it is translucent and filled with discernible fine structure. Its particles respond collectively while still allowing occultations to probe different depths. When Cassini watched a star pass behind the ring, small changes in received light traced changes in optical depth across kilometers and sometimes much finer scales. You would not hear Saturn's interior from within the C ring. The environment is effectively vacuum, and the density wave is not an airborne sound. It is a pattern of crowded and less crowded orbits. Yet the comparison to a record remains useful. The grooves are not carved into solid material. They are maintained in the spacing of moving ice. The C ring therefore joins two kinds of invisibility. It is partly transparent because its particles are dispersed, and it reveals motions inside a planet that cannot be seen directly. A faint band becomes a remote instrument. The B ring dominates the bright center of the system. It is broad, dense, and in many places highly opaque. For much of the Cassini mission, its mass and internal organization were among the most difficult ring properties to determine because the very density that made it bright also hid what lay behind and within it. Opacity does not mean solidity. The B ring remains a particle disk, but long sight lines encounter enough ice to block much of the light. Particles also gather into temporary elongated clumps called self-gravity wakes. Their mutual gravity draws them together while orbital shear and collisions prevent permanent collapse. The result is a continuously renewed texture of denser wakes and more open lanes. These structures can change the ring's brightness with viewing angle. Look across the long direction of many wakes, and they cover more of the background. Look through the gaps between them, and more light passes. A distant observer therefore measures not only how much material exists, but how that material is arranged. The B ring includes ringlets, waves, sharp boundaries, and regions whose optical properties differ markedly. Its outer edge is influenced by a strong orbital resonance with mimas. Each repeated gravitational pull helps define where the dense band ends and the Cassini division begins. Inside the band, local gravity competes with Saturn's tidal field. If the particles were far from Saturn and moving slowly relative to one another, some clumps might assemble into larger moons. Here, tidal forces, shear, and repeated collisions keep much of the material in a restless intermediate state. It gathers, it stretches, it separates. Then the pattern forms again elsewhere. This is one reason the rings can appear old in structure, even when their formation age remains disputed. Many fine patterns evolve quickly compared with the age of the solar system. A wake can be renewed on orbital timescales. A density wave can persist under repeated forcing. The appearance at any moment is not a frozen relic, it is current behavior. The B ring's brightness also affects the tidal scale illusion. It gives the eye a bold surface to follow across Saturn. A photograph compresses all particles, gaps, and wakes into luminous bands. The ring looks thick because its face is visually strong. Turn the same population edge on, and the broad display collapses. The densest ring becomes another narrow thread. Self-gravity wakes make that thread more complicated at close range. A wake is temporary, but not random. Nearby particles attract one another and form an elongated concentration. Saturn's differential gravity then stretches the group. Collisions keep the members from passing cleanly through one another, while shear prevents the concentration from becoming a permanent moon. The balance can repeat across the B ring like a grain in wood. Long wakes may align at similar angles relative to the orbital direction. The open channels between them allow some radiation to pass even where the overall region looks opaque. A measurement taken along one direction can therefore disagree with a measurement taken along another without either being wrong. This anisotropy is one reason mass cannot be read directly from brightness. A ring full of organized wakes may hide or reveal background light depending on angle. A smoother population with the same mass could look different. Models must include structure below the scale of a broad image. The B ring also demonstrates how close the disk may come to making larger bodies without completing the process. Clumps gather under mutual gravity. Tides stretch them. Impacts fragment them. The population hovers near a threshold, repeatedly assembling small temporary structures that do not survive as independent moons. Outside the B ring lies the most famous dark lane in the system. The Cassini Division is about 4,700 kilometers wide, large enough to fit the width of the continental United States from coast to coast with room left over. Yet calling it a gap can suggest too much emptiness. It contains ringlets and particles of its own, many with properties resembling the C ring. Its prominence comes from contrast. The dense B ring ends at the inner side. The bright A ring begins farther out. Between them, lower optical depth produces a dark arc in ordinary images. Through a telescope, the division seems like a clean cut. Cassini resolved it into a structured region. Mimas plays a central role near the inner boundary through a 2-to-1 orbital resonance. A particle at that location circles Saturn approximately twice for every one orbit of Mimas. The moon's gravitational tug therefore returns in a repeated rhythm. Small changes accumulate rather than canceling randomly. Resonance does not act like a hand pulling every particle outward at once. It changes orbital eccentricities and redistributes material through repeated encounters. Collisions spread those effects among neighbors. The resulting boundary can remain sharp even as individual particles enter, leave, collide, and follow new paths. Other resonances and waves cross the division. Narrow ringlets survive within it. Some edges are eccentric rather than perfectly circular, so their distance from Saturn changes slightly around the orbit. The dark lane is a region of organized scarcity, not absence. If you hovered above the Cassini division, the B ring would form a bright inner horizon, and the A ring a bright outer one. Between them, scattered ice would continue moving at many kilometers per second. The visual darkness would come from fewer reflecting particles along your line of sight, not from a shadow cast over an empty trench. This distinction applies throughout the ring map. A dark gap may be dynamically active. A bright ring may contain large empty volumes. Surface brightness translates population and geometry into an image, but it never tells the whole local story. Cassini first recognized the division with a 17th century telescope. The spacecraft carrying his name later crossed the distance from outline to mechanism. The old dark line remained. Its apparent simplicity did not. The A ring begins beyond the Cassini division and carries the bright main system toward its outer edge. It is less opaque than much of the B ring, but more visually substantial than the C ring. Across it run density waves, self-gravity wakes, embedded moonlets, and two especially recognizable gaps. The Enki gap is the wider of the two and contains the small moon Pan. The Keeler gap lies closer to the A ring's outer edge and contains Daphnis. Neither moon simply occupies a permanently vacant lane. Each gravitationally interacts with the gap edges and nearby particles, creating waves and changing structures as it travels. The A ring is also the home of many propellers. These features reveal bodies too small for Cassini's cameras to resolve directly in ordinary images. Their gravity opens paired disturbances much larger than the hidden object. A kilometer-scale moonlet can announce itself through a pattern extending for thousands of kilometers. This is a recurring feature of orbital systems. A small cause can create a large repeated signature when gravity acts over many encounters. The moonlet does not need to touch all the particles in its propeller. It changes nearby orbits. Differential motion stretches the response. The collective pattern becomes visible. Near the outer A ring, resonances with Janus and other moons help shape a remarkably sharp boundary. The edge is not a physical rim. It is a population boundary maintained by timing. Particles that wander across it encounter gravitational conditions that redirect or destabilize their paths. At Saturn's 2009 equinox, the A ring became a landscape of shadows. Moon-driven vertical structures that were nearly invisible under ordinary overhead lighting cast long dark lines. Daphnis produced some of the tallest. Other clumps and disturbances revealed that a sheet typically measured in meters could support localized relief measured in kilometers. The A ring therefore holds both the rule and the exception. Its ordinary distribution is extremely flat. Its active neighborhoods are wrinkled, lifted, and carved. The contradiction disappears once thickness is understood statistically. Typical does not mean everywhere. Thin does not mean featureless. From far away, the A ring is a pale band. From close range, it is a record of moons too small to see, poles too weak to notice once, and patterns too large to understand from one particle alone. Two small moons make the geometry visible. Pan travels within the Enki gap. Daphnis travels within the narrower Keeler gap. Both are embedded in the A ring region, and both continually exchange gravitational influence with the material at their gap edges. Pan is about 28 kilometers across at its widest dimension. Its unusual shape includes a pronounced equatorial ridge, built in part from ring material that accumulated around the moon. Cassini's close views made Pan resemble a central body surrounded by a smooth belt. That belt is evidence that the relationship runs both ways. Moons sculpt rings, and rings coat moons. Daphnis is smaller, about 8 kilometers across, but its orbit is slightly inclined and eccentric. As it moves through the Keeler gap, its gravity pulls on the nearby edges. The vertical component of that motion raises waves above and below the normal ring plane. Under low equinox sunlight, those waves cast shadows long enough to measure. One ridge associated with Daphnis rose about 4 kilometers above the surrounding material. That is hundreds of times the typical thickness of the main sheet. It is also tightly localized. Move away from the perturbed edge, and the ring returns toward its ordinary thin distribution. The scale offers a precise correction to flatness. A map can be flat at continental scale while containing mountain ranges. Saturn's rings can be about 10 meters thick in their ordinary sheet while carrying exceptional moon-driven structures kilometers high. The large relief occupies a small fraction of the radial and azimuthal extent. Pan's gap edges show waves in the plane. Daphnis adds strong vertical waves. Both demonstrate that a gap is an interaction zone. Particles approach, receive a small gravitational change, and continue on altered orbits. The next group arrives. The pattern renews with every passage. If you traveled alongside Daphnis, the moon would not leave one permanent wake frozen behind it. Inner material would move ahead relative to the moon. Outer material would fall behind. The resulting waves would stretch in opposite directions along the gap edges. The moons appear to command the ring, but they remain part of the same system. Saturn governs every orbit. The gaps provide room. The ring material supplies bright traces of otherwise invisible gravity. Just beyond the A ring lies a narrow feature that refuses to look simple for long. The F ring contains a bright core surrounded by strands, clumps, channels, and streamers. Prometheus repeatedly approaches it and draws material outward, leaving patterns that orbital shear later stretches and folds. Pandora travels nearby and also perturbs the region, but Cassini-supported models revised the older picture of two equal shepherds holding the ring neatly between them. Prometheus appears to provide the main confining influence on the bulk of the F ring, while the combined gravitational environment helps produce its chaotic structure. The distinction matters because the ring is not a rope held taut by two moons. It is a changing population responding to repeated close encounters. Prometheus can pull a streamer from the core. The particles then follow slightly different orbits. Over successive passages, channels and kinks develop at predictable intervals, but never form a perfectly static braid. Small bodies within the ring can collide or cluster. Dust spreads away from denser features. The narrow core remains identifiable while its surroundings change. Voyager images first made the braiding famous. Cassini showed a richer sequence of cause and response. Here the anchor returns in another form. Saturn's rings extend up to 282,000 kilometers from the planet, yet the main ring sheet is typically about 10 meters thick. The F ring sits outside that dense main sheet and has its own vertical and radial complexity, but it still occupies an extraordinarily small fraction of the dimension displayed across a portrait of Saturn. A camera sees the F ring as a luminous thread. A close observer would see a moving neighborhood with a bright central concentration. The thread's shape is continually redrawn by Prometheus, by local bodies, and by the differential speeds on either side of each orbit. This is not disorder without rules. The streamers recur because the same moon returns. The shearing follows the same relationship between radius and orbital speed. The clumps emerge from the same balance between gravity, collision, and tide. The F ring looks restless because its rules are visible on short timescales. Other rings change too, but their great width can hide local events. Here, narrowness turns motion into handwriting. Farther out lies the G ring, a broad and faint dusty region with a brighter arc embedded within it. For years, its source was uncertain because no large, obvious moon sat at the center of the entire ring. Cassini observations connected much of the material to a confined arc containing the small moon Aegeon and a population of larger source bodies. Micrometeoroid impacts strike those bodies and release dust. Once freed, the smallest grains respond not only to gravity, but also to radiation pressure, plasma, and Saturn's magnetic environment. They spread away from the source arc and contribute to the diffuse ring. The arc itself is maintained through a resonance involving mimas. The resonance keeps source material concentrated over a limited range of longitude, rather than allowing it all to smear immediately into a uniform band. Dust created there can still escape the confinement and populate the broader G ring. This gives the G ring a different life cycle from the main icy bands. It is not merely a leftover strip with a fixed inventory. It is supplied. Impacts create grains. Forces redistribute them. Other processes remove them. The visible ring is a standing population created by ongoing exchange. At ordinary exposure, the G ring is difficult to see beside Saturn's bright globe and main rings. Spacecraft images can emphasize it by using favorable lighting, especially when dust scatters sunlight toward the camera. Then a feature almost absent from the familiar portrait becomes a broad arc around the planet. You could cross its radial zone without encountering anything resembling the dense B ring. The distances between small grains would be far greater. Yet the total population across that enormous volume still catches enough light to define a ring. The G ring teaches a quieter version of the same lesson. Visibility does not measure solidity. A faint band can occupy a large region. A bright arc can depend on objects too small to dominate a distant image. A named ring can be the temporary balance between sources and losses rather than one enduring collection of particles. Outside it, the system becomes more diffuse still. The source arc adds a useful distinction between confinement and supply. Resonance can keep larger source bodies concentrated over part of the orbit, but newly created dust need not remain there. Small grains feel forces that barely affect Aegeon. The arc stays brighter because production is concentrated, while the surrounding G ring records the gradual escape of products from that neighborhood. This means a snapshot contains particles at different stages of one process. Some remain close to their parent bodies. Some have spread along Saturn orbit. Some are migrating radially. Some are approaching removal through collision or electromagnetic interaction. The G ring cannot be dated by following one grain because no grain represents the system's age. A grain can be newly released into a structure maintained for far longer. The same principle applies to the E ring, where fresh ice continually replaces material lost from the broad cloud. Rings with active sources behave like populations in steady flow. Their visible form can remain roughly stable when the rate of addition balances the rate of loss. Stability then describes a budget, not a permanent membership list. The E-ring extends through a vast region around Saturn and includes the orbit of Enceladus. Its particles are extremely small compared with many bodies in the main rings, and its material is broadly dispersed above and below the equatorial plane. The ring becomes most visible under lighting that favors forward scattering from fine ice grains. Cassini discovered the active source. Near the south pole of Enceladus, long fractures called tiger stripes vent water vapor, ice particles, and other material from an underground reservoir connected to the moon's internal ocean. Some grains fall back to the surface. Some escape Enceladus and enter orbit around Saturn, supplying much of the E-ring. This finding turned a diffuse ring into evidence of an active world. The material was not only debris from an ancient breakup, it was being produced during the mission. Cassini flew through the plume and analyzed its contents. The ring became an extended sample of Enceladus carried far beyond the moon. The E-ring's grains do not all remain indefinitely. Their paths are altered by Saturn's gravity, radiation pressure, plasma drag, electromagnetic forces, and encounters with moons. Continuous supply can maintain the population even while individual grains are lost. The geometry differs sharply from the A, B, and C rings. The E ring is much thicker and more diffuse. It does not fit the typical 10-meter description of the dense main ring sheet. This is why the title's claim must stay attached to the main rings, rather than every named component of Saturn's entire system. Inside the E-ring, Enceladus would appear as both moon and fountain. Its orbit carries it through the particles it helps create. Other moons within the region collect some of that bright ice on their surfaces. Material moves from interior ocean to plume, from plume to orbit, and from orbit to neighboring worlds. The journey has crossed from a collisionally flattened disk to a moon-fed cloud. Both are rings because their particles orbit Saturn. Their structures, sources, and vertical scales are otherwise very different. The alphabet hides that difference. Physics restores it. The outermost known component in this journey is almost detached from the familiar picture. The Phoebe ring is an enormous, extremely diffuse cloud associated with the orbit of the irregular moon Phoebe. NASA's Spitzer Space Telescope revealed it in 2009 through infrared observations of cool dust. The ring begins millions of kilometers from Saturn and extends across a region vastly larger than the bright main rings. Its particles follow retrograde orbits, moving opposite the direction of Saturn's rotation and the regular inner moons. The plane is also tilted relative to the main ring system because Phoebe itself travels on an inclined path. Dust is released from Phoebe and other irregular outer moons by impacts. As small grains slowly evolve inward, some encounter Iapetus, a moon with one remarkably dark hemisphere. Incoming material from the Phoebe ring population is a major contributor to that dark coating, though thermal processes on Iapetus help amplify the contrast after deposition. The Phoebe ring is too sparse to resemble a band from a nearby window. A particle could travel through a tremendous volume before meeting a neighbor. Infrared detectors found the collective thermal glow that visible light portraits missed. This remote ring changes the scale of the word ring one final time. The B ring is dense and bright. The F ring is narrow and perturbed. The E ring is a broad cloud of fresh ice from Enceladus. The Phoebe ring is a tilted outer dust population linked to irregular moons. All orbit Saturn. None are the same kind of place. If the main rings were removed from an image, the Phoebe ring would still surround the planet unseen by ordinary eyes. If the Phoebe ring vanished, the iconic bright disk would look unchanged. The most extensive component is not the most visible one. Saturn's architecture therefore runs from meters of typical thickness in the main sheet to millions of kilometers of diffuse outer space. The word system earns its weight. It includes bands, gaps, arcs, plumes, moons, and particles moving on paths that can even run in opposite directions. The famous rings are only the bright center of a much larger story. Return now to the main rings and look at the stripes within the stripes. Many are density waves, places where particles bunch together and spread apart under repeated gravitational forcing. They resemble ripples in an image, but no solid surface rises and falls as one piece. The pattern is carried by changes in orbital spacing. A moon can create such a wave through resonance. At a particular distance from Saturn, ring particles complete their orbits in a simple numerical relationship with the moon. Each time the geometry returns, The moon pulls in a similar direction. One tug is small. Thousands of tugs become organized. The wave's wavelength changes as it travels away from the resonance. By measuring that change, scientists can infer the ring's surface mass density and other properties. The ring becomes both subject and detector. Gravity supplies the repeated input. Particle spacing records the response. Some waves spiral around Saturn many times. A narrow radial slice shows alternating bright and dark bands, while the full pattern wraps across enormous distances. Differential rotation wins any non-circular disturbance tightly because the inner part moves ahead of the outer part. The same mathematics allows known moons to explain visible patterns and visible patterns to reveal unknown influences. Before a small moon is directly resolved, a gap edge or wave can betray its presence. Before Saturn's internal oscillations are fully understood, their gravitational signatures can appear in the C ring. You could pass through a density wave without crossing a crest like a boat. Instead, the number and arrangement of nearby particles would rise and fall. The relative motions might change. The probability of collision would vary. The visual brightness would pulse across the radial direction. These waves also show why no photograph is a simple inventory. A bright stripe may contain more particles, a different particle size distribution, a favorable viewing geometry, or some combination. Interpreting it requires models tested against occultations, images, thermal measurements, and radio data. Yet the underlying idea remains calm and precise. Repetition creates memory. A moon returns. Its pull returns. Particles respond. Their response becomes a pattern large enough to photograph. The rings are not passive ornaments around Saturn. They are a gravitational instrument with millions of moving parts. Density waves change how particles are crowded within the plane. Bending waves change the plane itself. A moon on an inclined orbit can pull ring particles slightly above and below Saturn's equator, creating a vertical ripple that winds through the disk. Because the ordinary thickness is so small, even modest vertical displacement can leave a measurable shadow under low sunlight. The wave need not raise every particle equally. It changes the average plane of nearby orbits. One region tilts upward, the next downward, and the pattern travels radially away from its resonance. Corrugations are related, but can carry the memory of a past disturbance. Imagine a broad ring temporarily tilted or warped by an external event. Saturn's non-spherical gravity makes tilted orbits precess at rates that vary with distance. The original bend wins into an increasingly tight spiral. Viewed later, it appears as alternating slopes and shadows. Cassini found corrugations in Saturn's rings and watched their wavelength evolve over time. Similar reasoning has linked disturbances in planetary rings to impacts or debris clouds, although identifying one unique cause can be difficult. The pattern preserves timing more readily than a complete history. Vertical waves remain exceptions inside a dominantly flat system. Their existence depends on the shared plane they disturb. Without a thin reference sheet, a displacement of a few meters or kilometers would not create such clear alternating geometry. The distinction between thickness and waviness helps again. A thin sheet of paper can be bent into a curve while remaining thin through its material. Saturn's ring plane can rise and fall while each local region still occupies a narrow vertical distribution. A bending wave changes where the middle lies. It does not necessarily turn the local swarm into a thick cloud. At a gap edge, Daphnis can produce both radial and vertical structure. Farther away, a resonance can launch a broader bending wave. In the D and C rings, corrugations can extend across thousands of kilometers, while their vertical amplitude remains comparatively small. Saturn's rings are flat, but not geometrically mute. They tilt, ripple, and wind. Their deviations are small beside their width and large enough to reveal the forces that made them. The vertical motion of one particle can be pictured as a slow crossing of the reference plane, twice per orbit. It rises on one side of Saturn, passes through the plane, descends on the other, and returns. Neighboring particles with slightly different precession rates gradually lose alignment, winding a broad bend into a tight corrugation. Collisions oppose that persistence. When particles on differently tilted paths meet, their vertical components are reduced on average. A bending wave must therefore be continually forced or recently created strongly enough to remain visible. Its shape reflects the competition between excitation and damping. Researchers can use the winding rate as a clock because Saturn's gravity field determines how quickly orbital planes precess at different radii. If a corrugation's wavelength is measured at 2 times, the change helps test when a disturbance occurred. The inference still depends on a model, but the rings preserve a quantitative trace. This is a form of memory without fixed matter. The particles observed today need not be the same neighbors that first received the disturbance. The pattern passes through the population as each member contributes its orbit to the larger geometry. Some of the A-ring's most distinctive structures look like paired wings. Cassini scientists call them propellers. Each is produced by the gravity of an embedded moonlet larger than an ordinary ring particle, but too small to clear a complete circular gap around Saturn. The moonlet perturbs particles passing on its inner and outer sides. Small depleted regions open near its orbit. Orbital shear stretches those regions in opposite directions. Denser wakes gather around them. From above, the combined disturbance resembles a propeller with 2 offset blades. The resemblance stops there. The feature does not spin about the moonlet like a mechanical propeller. It is an orbital pattern renewed as new particles enter the neighborhood and old ones move away. The moonlet travels around Saturn, carrying the center of influence with it. Cassini observed propellers thousands of kilometers long. The hidden bodies responsible were estimated around a kilometer in scale for the larger examples. That gap between cause and signature is one of the ring system's most useful magnifications. Gravity turns a body below direct imaging resolution into a pattern a spacecraft can track. Several large propellers received informal names from aviation, allowing researchers to follow their locations over multiple years. Their orbits did not always behave as a simple isolated 2-body calculation predicted. Interactions with surrounding ring material can exchange momentum with the moonlet, nudging its path. This creates a bridge between the smallest visible particles and recognized moons. At one end are grains controlled strongly by non-gravitational effects. At the other are bodies such as Pan and Daphnis that maintain complete gaps. Propeller moonlets occupy the middle, massive enough to organize neighbors, but not massive enough to dominate a full band. If every embedded object were removed, the A-ring would lose more than a set of tiny points. It would lose long paired structures and some of its evolving texture. The ring's appearance is larger than the inventory of visible bodies because each body carries a gravitational neighborhood. Propellers make the invisible legible, not by adding light, but by rearranging ice. The B ring contains another class of structure that does not fit a purely gravitational picture. Spokes are radial markings that can stretch more than 16,000 kilometers, longer than Earth's diameter. Voyager first photographed them. Cassini watched them appear, fade, and change with Saturn's seasons. Scientists think the spokes consist of very small icy grains lifted above the main ring by electrostatic forces. Charged particles respond to Saturn's magnetic environment more strongly than house-sized blocks do. A cloud of grains raised slightly above the dense background changes the way light is scattered, producing a dark or bright radial feature, depending on viewing geometry. The spokes can form over hours and disappear over similarly short intervals. Their rapid change separates them from long-lived ring boundaries. They are weather-like in appearance, though there is no air carrying them and no atmospheric cloud in the ordinary sense. Their radial shape is also temporary. Differential orbital motion should shear a fixed radial line because the inner end circles faster. A spoke can remain recognizable only while electromagnetic organization and particle evolution compete with that shear. Eventually, the pattern disperses. Season matters because sunlight changes particle charging and the relationship between the rings and Saturn's magnetosphere. Spokes were absent or difficult to detect during part of Cassini's early observations, then returned as the planet moved toward equinox. The cycle is not understood in every detail, but the connection shows that the rings respond to more than gravity and collision. You could imagine entering a spoke as a change in the population of fine grains around the main sheet. It would not be a rigid wall crossing your path. Its edges would be diffuse. Its visibility would depend on where the sun, the particles, and the observer were aligned. The main rings are built primarily by orbit, but the smallest members can listen to electric and magnetic forces that larger bodies barely notice. Particle size decides which influence becomes important. A single image of a spoke looks like a dark brush mark. Its real structure is a temporary suspension of charged ice above a moving disk. On August 11, 2009, Saturn reached equinox while Cassini was there to watch. Sunlight struck the ring plane almost edge-on. The broad faces received little direct illumination, and familiar bright bands dimmed. Features that normally blended into the disk began casting long shadows. The event comes only about twice during Saturn's 29.4-year orbit, roughly once every 15 Earth years. From Earth, a similar geometry can make the rings appear nearly absent. From Saturn orbit, equinox transforms the system into a laboratory for vertical measurement. A low sun magnifies height. A ridge only meters high can cast a shadow far longer than itself. A moon rising kilometers above the plane produces a dark line extending across the surrounding ring. By measuring shadow length and solar angle, scientists can estimate vertical relief that would be nearly invisible under overhead light. The overall result confirmed the defining proportion while revealing its exceptions. Saturn's rings extend up to 282,000 kilometers from the planet, yet the main ring sheet is typically about 10 meters thick. Across most of that enormous face, little rose high enough to cast a dramatic shadow. In disturbed zones, however, clumps and waves climbed far above the ordinary sheet. Cassini also measured ring temperatures. With sunlight reaching only the edges, parts of the system cooled. The A ring fell to about minus 230 degrees Celsius, the lowest temperature Cassini recorded there. Thermal behavior helped constrain particle properties because small grains and larger blocks warm and cool differently. The equinox image reverses the usual portrait. Under normal light, the broad horizontal surface dominates and vertical structure hides. Under edge lighting, the surface fades and height becomes visible. The rings trade brightness for information. This is why thinness is not only an impressive number, it is an observational tool. The closer the system comes to a perfect plane, the more clearly a departure announces itself through shadow. For a brief season, Saturn's most visible feature nearly disappeared. In that disappearance, Cassini saw more. The most striking equinox exceptions appeared near moons and sharp edges. Along the Keeler Gap, Daphnis raised waves as high as about 4 kilometers. Elsewhere, clumps at the outer B ring cast shadows, indicating relief measured in kilometers. NASA compared some of the largest features with terrestrial mountain ranges. These heights sound incompatible with a ring sheet typically about 10 meters thick. They are compatible once location and definition are kept clear. The 10-meter value describes the ordinary vertical distribution of particles in the main rings. A moon, resonance, or concentrated clump can drive a small region far above that baseline. Think of the ratio across the entire disk. A 4-kilometer ridge is large vertically but narrow in area. The main rings extend across hundreds of thousands of kilometers. One disturbed edge occupies only a minute portion of the full surface. Most locations remain close to the plane. The exceptional structures also reveal strength without solidity. A Daphnis wave is not held up by a continuous sheet. Individual particles follow inclined orbits after gravitational encounters with the moon. Their coordinated paths create a ridge. As they move away and collide, the pattern changes. At the outer B ring, self-gravity and resonant forcing can gather particles into dense clumps. Their collective gravity lets them rise and persist differently from isolated grains. The clumps are temporary architecture, built from pieces that may later separate and join other structures. If the rings were hundreds of kilometers thick everywhere, equinox shadows from a 4-kilometer feature would blend into a broad vertical haze. Because the background is so thin, the same ridge becomes unmistakable. Flatness gives contrast to relief. This offers the most precise answer to the visual objection. Images often show the rings with exaggerated thickness so viewers can see them. Scientific diagrams may separate bands and gaps more than a true scale view permits. Those choices are useful, but they can make the system seem like a thick disk. The real rings are thinner and locally rougher. Both statements are true. The roughness is written on a plane whose ordinary depth would fit inside a modest building. Saturn's actual tilt of about 26.7 degrees gives the planet seasons broadly comparable in geometry to Earth's, though each season lasts more than 7 Earth years. The rings share Saturn's equatorial plane, so their illumination changes dramatically across the 29.4-year orbit. During one half of the Saturnian year, the sun lights the northern face more directly. During the other half, it lights the southern face. At equinox, illumination slides across the edge. The shift changes temperatures, shadows, spoke activity, and the brightness seen from Earth. Ring particles respond according to size, spin, composition, and whether neighboring particles shade them. A small grain can change temperature quickly. A larger icy block stores heat and releases it more slowly. Dense regions exchange radiation among closely packed surfaces, differently from sparse regions. Cassini's infrared instruments measured these patterns over years. One especially puzzling result appeared around equinox, when part of the A ring remained warmer than simple models expected. Researchers used the anomaly to investigate the internal structure and thermal inertia of particles, including the possibility that some bodies contain dense cores beneath fluffier outer layers. Temperature therefore reveals more than distance from the sun. It records how particles are built and arranged. Two neighboring ringlets under the same sunlight can cool differently because their typical particle sizes or surface textures differ. The seasonal cycle also changes what an observer can see. Backlit dust becomes bright when it scatters sunlight forward. Opaque bands reveal their darker, unlit faces. Shadows from Saturn cross the rings. Shadows from the rings stripe Saturn's atmosphere. The iconic view is a sequence, not a fixed pose. You could return to the same point in the ring plane 7 Earth years later and find the sun arriving from a markedly different angle. The particles would still orbit in hours. The planet would still turn quickly, but the long seasonal geometry would have redrawn every shadow. Fast orbits live inside slow seasons. A piece of ice can circle Saturn thousands of times while the sun barely changes its elevation over the rings. The system carries both clocks at once. Seasonal lighting affects Saturn as well as the rings. The broad ring sheet casts shadows onto the planet's upper clouds, creating dark bands whose position migrates with the sun. Saturn casts its own vast shadow across the rings on the night side. Particles enter that darkness, cool, and later return to sunlight on the other side of the orbit. An individual grain can therefore experience a rapid day-night cycle inside the long seasonal one. Its thermal response depends on how quickly it spins and whether neighbors block the view. Dense wakes create local shade. Sparse regions expose more surface directly to space. From Earth, the opening angle changes gradually. Years with widely open rings produce the classic broad view. Near a plane crossing, their light weakens and small moons can appear detached along a thin line. Observers across generations have watched this cycle without changing telescopes, simply because Saturn moved along its orbit. The rings make Saturn's seasons visible at a distance. A planet's axial tilt becomes an expanding ellipse, a narrowing line, a reversal of the illuminated face, and another slow opening. Cassini often studied the rings by looking through them. During a stellar occultation, a chosen star passed behind the ring system from the spacecraft's viewpoint. As the star's light crossed each band, particles blocked and scattered part of it. The changing signal became a narrow scan through the rings. Ultraviolet and infrared instruments could measure different properties. Radio occultations use transmissions from Cassini to Earth at multiple wavelengths. Large particles, small particles, dense wakes, and open gaps affected those signals differently. The method turns distance into detail. A camera pixel may combine light from a broad area. An occultation samples a thin path defined by the apparent motion of a star or radio beam. Fine ringlets and sharp edges appear as rapid changes in received intensity. One occultation does not produce a complete map. It is closer to drawing a line across a landscape in darkness and recording every obstruction. Many lines taken at different times and angles reveal how structures vary with longitude, radius, and viewing geometry. Occultations helped measure the size distribution and arrangement of particles. They showed that some apparently smooth regions contain repeated wakes. They traced density waves too fine for ordinary wide images. They also let researchers compare the same feature at different wavelengths. The star remains far beyond Saturn. Its light may have traveled tens or hundreds of years before reaching the rings, then been interrupted for a fraction of a second by local ice. Cassini recorded that interruption and turned it into a measurement of a particle population no instrument could collect piece by piece. This method respects the true nature of the system. It does not treat the rings as a painted surface. It asks how much light survives a path through moving material. The answer depends on empty space as much as ice. Every bright recovery marks a more open interval. Every dimming marks more obstruction. A distant point of light becomes a ruler sliding behind Saturn's thinnest structure. The ring system's brightness does not reveal its mass directly. A vast population of small reflective grains can look brighter than a darker population containing more material. For decades, estimates of Saturn's ring mass depended heavily on models of density waves, opacity, and particle arrangement. Cassini's grand finale provided a new measurement. During 2017, the spacecraft repeatedly passed between Saturn's atmosphere and the D ring. Radio tracking from Earth measured tiny changes in its motion. By separating the gravitational pull of Saturn from the additional pull of the rings, researchers estimated the ring system's total mass. The published result was about 1.54 times 10 to the 19th kilograms, with an uncertainty of roughly 0.49 times 10 to the 19th. That is about 0.41 times the mass of Mimas, again with substantial uncertainty. The number is enormous by human standards and small compared with Saturn. If all that material could be assembled into one body, it would make a modest moon rather than another planet. Spread across the ring plane, the same mass produces a structure wider than Saturn itself and thin enough to nearly vanish edge-on. The measurement mattered for age models. A massive ring can absorb dark contamination longer before its overall composition changes. A lower mass ring reaches a given pollution fraction sooner. Knowing the mass therefore narrows some histories, but it does not by itself state when the rings formed. The grand finale also sampled material flowing from the inner rings into Saturn and measured the planet's gravity and magnetic field in unprecedented detail. Cassini approached the system it had studied for 13 years, using its final orbits to examine the boundary between ring and atmosphere. On September 15, 2017, the spacecraft entered Saturn's atmosphere and ended its mission. The controlled descent protected potentially habitable moons from accidental contamination. Its final radio signal took more than an hour to cross the distance back to Earth. The rings remained. Their mass had become better known. Their origin had not become simple. Weighing the rings required unusually careful separation. Cassini felt Saturn's enormous gravity, the smaller pull of the rings, the gravity of nearby moons, and non-gravitational forces acting on the spacecraft. Radio signals tracked tiny velocity changes through the Doppler effect. Researchers fitted those observations with models of Saturn's interior and atmospheric winds. The uncertainty in the final ring mass is therefore part of the result, not a footnote to remove. The ring's pull is small beside the planets. Saturn itself is not a simple spherical body. It rotates rapidly, bulges at the equator, and contains deep flows that alter its gravity field. The grand finale trajectory was valuable because passing inside the rings changed the geometry enough to separate contributions more effectively. Mass then connects to several other questions. It changes how quickly a disk spreads. It changes how a given amount of dark dust affects average composition. It changes what kind of parent body could have supplied the material. One measured quantity narrows many models at once. Cassini could not rewind the system. It could improve the boundary conditions for every proposed history. That is often how planetary exploration advances, not by producing one final scene, but by making the range of possible scenes smaller. For much of planetary science, Saturn's rings could be imagined as ancient companions, left over from the formation of the planet 4.5 billion years ago. Their brightness created a problem for that picture. Interplanetary dust continually arrives at Saturn. Much of that dust contains darker, non-icy material. Over immense time, impacts should mix contamination into the ring particles and reduce the purity of their visible ice. Cassini measured several quantities needed to turn that intuition into a model. Its cosmic dust analyzer counted incoming micrometeoroid particles in the Saturn system. Other instruments constrained the fraction of non-icy material in different rings. The grand finale gravity experiment estimated total ring mass. In 2023, researchers using the final Cassini dust measurements reported an incoming mass flux that, under their assumptions, implied an exposure time of no more than about 100 to 400 million years. Related simulations that included pollution, spreading, and transport also favored a ring system exposed for less than a few hundred million years if the measured flux remained broadly persistent. That is young compared with Saturn. A 100 million year ring would have formed after dinosaurs had already appeared on Earth. Even 400 million years is less than 1/10 the age of the solar system. The argument does not rest on brightness alone. Ring mass affects the dilution of contaminants. Ballistic transport moves impact debris radially. Viscous spreading changes surface density. Material falling into Saturn provides another measure of ongoing loss. When these processes are combined, some models produce a comparatively young temporary ring system. Young does not mean recently created in human terms. 100 million years contains more than 3 trillion seconds. The rings could complete an immense number of orbits and build complex structures during that interval. Density waves, wakes, and moon interactions do not require the disk to be primordial. The youth interpretation also separates Saturn from its ornament. The planet formed with the solar system. The present bright rings may have appeared much later, perhaps after an icy moon was disrupted, or two bodies collided within the region where Saturn's tides prevented easy reassembly. Yet every step contains assumptions. The dust flux measured during Cassini's years must represent much longer intervals. Contaminants must remain in the rings in modeled proportions. Impact products must be transported and lost in understood ways. The starting mass and composition must lie within a chosen range. The evidence is serious. The date is not a direct observation. Cassini measured a present system, and models carry that system backward through time. The most honest age of Saturn's rings is not one number. It is an argument connecting measurements to histories that cannot be watched directly. New work has challenged a key link in the young ring interpretation, the assumption that incoming dark material remains efficiently mixed into the visible ice. In high-speed impacts, micrometeoroids can vaporize. The impact products become charged, interact with Saturn's magnetic field, fall toward the planet, or escape the local ring population. Modeling published in 2024 suggested that relatively little dark material may remain embedded in the rings after some impacts. Clean-looking ice could therefore resist pollution more effectively than earlier simple estimates assumed. If that process is strong, brightness becomes a less direct clock. An old ring might look younger because it sheds or separates much of the contamination that would otherwise darken it. The model does not prove the rings formed with Saturn. It shows that one piece of evidence can support more than one history. Exposure age, formation age, and particle age also need separation. The current visible material may have been recycled through collisions. An ancient ring system could lose and reaccrete particles. A younger present disk could contain old ice inherited from a destroyed moon. Asking how old the rings are can mean how long the system has occupied this region, when the parent body formed, or how long the current surfaces have been exposed. The measured mass still constrains possibilities. The observed dust flux still matters. The flow of ring material into Saturn is real, but combining those facts requires a model of how the disk spreads, darkens, and renews itself over hundreds of millions or billions of years. Scientists test these histories against more than color. They compare the sizes and compositions of small moons, the current radial mass distribution, the rate of inward transport, the persistence of narrow structures, and dynamical simulations of disruption. No single observation has ended the debate. This uncertainty belongs in the story because it is productive rather than empty. Cassini did not fail to answer the H question. It transformed a vague question into measurable disagreements. How much dust arrives? How much stays? How quickly mass moves? How a disrupted body spreads? Each can be improved. The rings are either a remarkably well-preserved ancient structure, a comparatively recent product of destruction, or a system whose material has been renewed enough to blur that distinction. Current evidence narrows the range without making the origin seen visible. Their brightness is a clue. It is not a birth certificate. The disagreement can be narrowed by future measurements. A new mission could sample particles directly in multiple rings, map contamination with higher spatial resolution, and measure present mass transport across seasons. Better laboratory experiments could test what fraction of an impactor remains attached to cold porous ice at Saturnian speeds. Longer observations could show whether today's influx is typical. Until then, the evidence keeps a specific shape. The young estimate follows from measured dust, measured contamination, measured mass, and modeled retention. The older possibility follows from a different modeled retention efficiency and a longer dynamical history. Neither can be reduced to color alone. The uncertainty is not ignorance of every relevant fact. It is sensitivity to processes that operate too slowly and too far away to observe from beginning to end. Any origin scenario must explain four broad properties at once. The rings contain abundant water ice. They occupy a region close to Saturn where tides are strong. Their present mass is a fraction of Mimas's, and their particles are distributed in a flat disk rather than assembled into one large moon. One family of models begins with a moon. An icy satellite passes too close to Saturn, collides with another body, or has its outer layers stripped by tides. Debris spreads along the parent orbit. Collisions reduce eccentricity and inclination. Differential rotation stretches fragments into a disk. Over time, the material separates into rings, gaps, and small moons. Another family begins earlier, while Saturn and its satellites are forming. Material inside the effective Roche region cannot easily gather into a large coherent moon because Saturn's tidal pull overcomes weak self-gravity across a loose body. Outside that region, clumps can survive more readily and accrete. A primordial disk might therefore leave rings inside and moons beyond. The Roche boundary is not one simple painted circle. Its location depends on density, internal strength, spin, and whether the body behaves like a fluid collection or a strong solid. Small icy objects can survive inside a classical fluid Roche limit. Loose aggregates behave differently from monolithic blocks. The modern ring moon boundary may also migrate. Ring material spreads outward through collisions and gravitational transport. At the outer edge, particles can gather into moonlets once tides weaken enough. Those moonlets can move away through interactions with the disk, leaving room for more material to assemble. In that picture, rings make moons. Elsewhere, moons make rings by shedding plumes or impact dust. Enceladus supplies the E ring. Aegeon and neighboring bodies help supply the G ring. Phoebe and irregular moons supply remote dust. There is no requirement that every named ring share one origin event. The bright A, B, and C rings may be closely linked to one major disruption. The diffuse rings clearly depend on continuing sources. Saturn's full ring system is a collection of histories bound to one planet. Any reconstruction must also survive the mass loss clock. A more massive original ring could spread and drain until reaching today's state. A recent disruption could begin closer to the present mass. The unknown starting point changes the inferred age. Origin models therefore run forward as well as backward. Begin with a moon, a disk, or a collision. Apply Saturn's gravity, tides, impacts, and transport. Then ask whether the result resembles the rings Cassini measured. The answer is not chosen for elegance. It is earned by arriving at the right mass, brightness, composition, and structure at the same time. A disrupted moon would not become the present rings immediately. The first debris cloud could contain large fragments on eccentric and inclined paths. Collisions would grind and redistribute them. Some material would fall into Saturn. Some would escape. Some would settle towards circular orbits and spread radially. Composition creates another filter. Saturn's bright rings are rich in water ice. A parent body with a large rocky core must lose or hide that rock in a way consistent with current measurements. Tidal stripping might remove an icy mantle while leaving a denser core to fall into Saturn. A collision might separate materials imperfectly. Each scenario predicts a different starting inventory. Small moons near the rings offer additional evidence because their densities, shapes, and coatings record assembly from ring material. Pan's ridge and Atlas's equatorial shapes suggest accretion in a disk. Their existence shows that the boundary between ring particle and moon is not absolute. The origin problem is therefore not a search for one dramatic breakup alone. It is a sequence: disruption, flattening, sorting, spreading, loss, and reaccretion. The event creates material. Orbital evolution creates the ring system. The rings are losing material. Charged water products move along Saturn's magnetic field into the upper atmosphere. Dust and gas also fall inward near the equator. Cassini and Earth-based observations have measured different parts of this exchange, often grouped under the phrase ring rain. One NASA-supported estimate compared the water product flow with filling an Olympic-sized swimming pool every half hour. Extrapolated at that reported rate, the rings would lose a substantial fraction of their material over hundreds of millions of years. When additional influx measured during Cassini's final passes is included, some worst-case estimates fall below 100 million years. Those are conditional lifetimes, not scheduled dates. Rates can vary with season, particle supply, and processes not fully measured. The current inflow may not have remained constant across the past or continue unchanged across the future. Different measurements also trace different forms of material and different routes into Saturn. The safe conclusion is narrower. The ring system is not closed. Material crosses inward. Water and dust enter the atmosphere. The rings must either be replenished, evolve, or gradually diminish. Loss happens alongside spreading. Collisions transport angular momentum. Some material moves inward and eventually encounters Saturn. Some moves outward toward regions where moonlets can assemble. Micrometeoroid impacts add contaminants while ejecting other material. Moons contribute grains to diffuse rings and remove grains from them. The iconic shape is therefore a flow pattern. It can remain recognizable while its members change, just as a river keeps its course while new water passes through. The comparison stops at the mechanism because ring particles orbit rather than running downhill. But the distinction between stable form and changing inventory is the same. Saturn's rings extend up to 282,000 kilometers from the planet. Yet the main ring sheet is typically about 10 meters thick. Across that immense shallow architecture, loss is occurring particle by particle. No visible edge races inward. No band disappears between photographs. The change is distributed across timescales longer than a civilization. If the rings are young, ring rain may be one part of a brief, bright chapter. If they are old, replenishment and pollution resistance must help explain their persistence. In either case, permanence is an appearance created by slow change. The rings are present now. That fact need not last forever to be profound. Loss also links rings to atmosphere. Material that begins as solid water ice can be broken into molecules, ionized, guided along magnetic field lines, and detected above Saturn. The boundary between orbit and planet is permeable. A ring particle does not need to fall as an intact block to leave the disk. At the same time, outward moving material can cross a different threshold and contribute to moon formation. The system leaks in both conceptual directions, inward toward atmosphere and outward towards satellites. Its present width is the visible middle of that transport. This flow prevents a simple ending. Saturn may never wake one morning without rings. Bands can thin, spread, and change composition at different rates. Diffuse components can continue as the bright main disk fades. The future, like the origin, is a sequence rather than one event. The journey can now be assembled into one imagined passage. Begin above Saturn's north side, far enough away that the bright main rings form a complete ellipse. The planet turns below in 10.7 hours. Cloud bands move through amber light. The ring plane cuts across the equator with geometrical precision. Approach from above rather than edge on. The ellipse broadens toward a circle. The B ring dominates the center of the disk. The Cassini Division draws a dark arc. The A ring carries the bright surface outward. Beyond it, the F ring becomes a narrow line that changes shape under Prometheus's repeated pull. No engine is aimed through the dense bands. This is a conceptual route, free from the danger that real ice would present to a spacecraft. The view slows enough to separate particles that ordinary vision blends. The first bodies appear as points. Then the points acquire size. Pale blocks turn in sunlight. Fine grains brighten when viewed toward the sun. Between them lies black space. Every particle travels sideways at orbital speed, and the inner members gradually move ahead of the outer members. Cross a density wave. Neighboring orbits crowd together, then spread. Cross a propeller. A hidden moonlet sits within paired disturbances far longer than its own body. Cross a spoke. Charged grains rise slightly above the dense background and then disperse over hours. Near the Keeler gap, Daphnis moves along its narrow lane. Its gravity lifts a rippled edge. The tallest wave reaches kilometers above a sheet that ordinarily occupies meters. The exception looks enormous because the reference plane is so exact. Turn toward the Cassini Division. Its darkness resolves into a lower density region containing ringlets and moving particles. Beyond it, the B ring gathers into self-gravity wakes. The apparent surface breaks into alternating concentrations and openings. Continue inward through the C ring, where starlight could pass between and through the population strongly enough for occultations to read its structure. The faint D ring approaches Saturn. Below lies the gap Cassini crossed 22 times during the grand finale. Now reverse the scale and rise. Individual blocks become flecks. Flecks become brightness. Gaps become dark curves. The vertical distance collapses first. Soon the main rings are once again a broad visual object. From far above, the journey looks like a surface. From within, it was always a collection of paths. The scale transition also changes Saturn itself. From Earth, planet, and rings fit within one telescopic field. Near the main rings, Saturn's curved limb fills a large fraction of the sky. The planet's shadow becomes a region you can enter. The A, B, and C rings extend toward distant horizons in both directions while remaining vertically confined around you. Because there is no air, distance would be difficult to judge by haze. A house-sized ice block could appear small and near or large and far until its motion gave another clue. Sunlit faces would be pale. Shadowed faces would blend into space. Fine dust would brighten most strongly in selected directions. Time would restore the geometry. Inner particles would move consistently ahead. Gap edges would repeat their waves. A moon would return on schedule. The swarm might seem chaotic over seconds, but the pattern would become orderly over orbits. Then distance would erase the members again. This is the visual rhythm of every ring image, individual motion compressed into collective form. The closer view is not more real than the distant one. Each reveals a different level of the same system. The imagined passage ends where the scientific method begins, by changing scale without changing the object. At one scale, brightness and symmetry are the facts. At another, collisions and gaps are the facts. At another, micrometeoroid flux and mass transport are the facts. A complete account must allow all three to remain true. That is why Saturn's rings reward patient attention. Their first impression is immediate and familiar. Their explanation moves steadily away from the familiar through geometry, granular motion, resonance, electromagnetism, thermal physics, and planetary history. The icon survives every correction. It simply becomes more precise. We have talked about a ring system that spans a planetary distance while keeping its ordinary main sheet within the height of a modest building. We have talked about Galileo's unresolved companions, Huygens' detached flat ring, and Cassini's dark division, each observation moving closer to the geometry that later spacecraft could measure. We have talked about water ice ranging from grains to house-sized blocks and larger bodies, bright enough in aggregate to turn separate particles into continuous-looking bands. We have talked about inner material moving faster than outer material, about a straight pattern shearing into a curve, and about collisions removing random vertical motion while preserving the shared circulation around Saturn. We have talked about the D ring near the atmosphere, the translucent C ring, the crowded B ring, the structured Cassini division, and the A ring crossed by gaps, waves, moonlets, and propellers. We have talked about Pan wearing material gathered near its equator, and Daphnis raising the Keeler gap's edges kilometers above the ordinary plane. We have talked about Prometheus drawing streamers from the narrow F ring, about Aegeon and source bodies feeding dust into the G ring, about Enceladus supplying the E ring from an active ocean world, and about the remote Phoebe ring moving through a tilted outer darkness. We have talked about density waves, recording repeated gravitational pulls, and ring seismology translating oscillations inside Saturn into patterns outside it. We have talked about spokes longer than Earth's diameter, temporary populations of charged ice that appear and fade with a rhythm linked to Saturn's seasons. We have talked about equinox, when sunlight reaches the ring's edge on, broad brightness falls away, and small heights cast long shadows. We have seen the A ring cool to about minus 230 degrees Celsius and the Daphnis wave rise about 4 kilometers. We have talked about Cassini watching stars through ice, measuring the mass of the rings through gravity, and ending its mission in Saturn's atmosphere after 13 years in orbit. We have talked about a measured ring mass near 1, 54 times 10 to the 19th kilograms, large enough to build an immense bright disk and only a fraction of the mass of Mimas. We have talked about youth supported by dust flux and pollution models, age preserved as a possibility by models of pollution resistance, and the careful distance between exposure age and formation age. We have talked about material arriving, material escaping, and water products falling into Saturn as ring rain, a stable image, a changing inventory. Every piece returns to the same central fact. The rings are not one object in the ordinary sense. They are order shared among separate objects. Their beauty comes from distance, where motion becomes pattern. Their science comes from approaching closely enough to see the motion again. The title can now be answered plainly. Saturn's main rings are thinner than most images make them seem. They extend across hundreds of thousands of kilometers, yet their ordinary vertical thickness is typically about 10 meters. They are not perfectly flat. Near moons and disturbed edges, particles can rise kilometers above the plane. The exceptional ridges do not weaken the answer. They show how remarkably flat the rest of the system is. To fall asleep inside them, in the language of the roadmap, is to enter an idea rather than a habitable place. A real passage through the dense rings would expose a spacecraft to dangerous particles. There is no platform, no shelter, and no air. The safe journey is the one made through scale, orbit, and light. From that imagined position, Saturn fills much of the sky. The planet has no solid visible surface, only layered clouds and deeper fluid under pressure. The rings do not arch overhead like a roof. They spread outward through the plane as a population of illuminated paths. The inner pieces move ahead. The outer pieces fall behind. A moon returns to the same resonance. A wave is renewed. A grain receives charge and rises into a spoke. Enceladus releases fresh ice. A micrometeoroid adds dust. Somewhere near Saturn, water products leave the rings and enter the atmosphere. No particle understands the pattern. Each follows local forces. Together, they create edges sharper than a mountain horizon, gaps wider than nations, and bands visible across more than 1 billion kilometers of interplanetary space. There is a philosophical quiet in that arrangement. Large order does not always require a large solid thing. It can emerge from many small bodies obeying the same relationship. A ring is not less real because its members change. Its reality lies in the pattern they continue to make. Human structures often feel permanent because their change is slow compared with one life. A coastline moves, a mountain erodes, a language replaces its words while keeping a recognizable shape. Saturn's rings extend that thought across orbital time. Their inventory changes. Their portrait persists, whether the bright main rings formed a few 100 million years ago or carry a much older history remains unsettled. Either answer changes the meaning, but not the present view. If they are young, we live during a temporary luminous chapter in Saturn's long existence. If they are ancient, we are seeing a system that has found ways to preserve or renew bright ice through billions of years of impacts and loss. Both possibilities make the present encounter rare in a different way. Cassini spent more than a decade turning the icon into measurements. A dark line became a particle distribution. A ripple became a resonance. A shadow became a height. A radio shift became a mass. The mission did not remove mystery. It gave the mystery boundaries. The most important boundary is the plane itself. Collisions continually reduce the motions that would thicken it. Saturn's gravity keeps particles falling around the planet. Moons disturb selected regions. Electromagnetic forces lift the smallest grains. The sheet survives not by resisting change, but by absorbing change into orbit. Saturn's rings extend up to 282,000 kilometers from the planet, yet the main ring sheet is typically about 10 meters thick, wider than a world, thinner than a building, ice in darkness, motion made visible, a temporary form, a precise plane. Good night.